Okay. Assalamualaikum warahmatullahi wabarakatuh and good evening. I hope you can hear my voice, right? Yes or no?
Yes, better.
Okay, good. Um, uh, I've seen a few of international students. I would like to let you know that uh, please make sure your name in the list for the lecture attendance. The link that I sent you, the Google spreadsheet, please make sure you have your name either in one of the session. Because I know you registered through your OSI. OSI system is just for the sake of registration only. So it doesn't matter you are in G1, G2 or G3, please again choose your session, session or and tutorial session that you would like to join for this course. Because I'm going to use the list for the attendance purpose. So I noticed that there are few international students who hasn't registered to any of those group. So please do so. Right now you can't really do it on your own. You have to DM me privately. Okay, enough on that. So today we are going to continue on still on chapter 1, but on the second part of the lecture 1. So I'm going to turn off the camera, uh, but please listen, of course. And okay, I'm going to share the screen. So hopefully you could see something. You could see the screen loading. The PPT slide that we stopped on the last lecture. So okay, I did the introduction on the basic signal operations on the last lecture, whereby you basically learn about the additions, multiplications, simple operation for signal. Second, you know as well amplitude scaling. So normally for amplitude scaling, you have a certain constant, for example A or gain in front of the signal. And now today, we are going to see time scaling. Um, this is time scaling for continuous time signal, CT signal, and this is for the discrete time signal, or DT. So for time scaling, so basically you could also say time scaling as the compression or the uh, expansion of the signal. So for CT signal or continuous time signal, you could see that YT, your signal, which is equal to X AT. So whenever you have a certain constant next to T, so you know that this is time scaling. So for this case, you could say that you are having, in this case, whenever you see uh, A is a positive number or greater than 1, uh, this gonna be compression. So whenever A here is greater than 1, that's gonna be compression. And if A is less than 1, it's going to be expansion. So in this case, for these examples, you have the example for continuous time signal here. It somewhat look like a triangular signal. So whenever you have the scaling time of, which is in this case t over 2, so you are somewhat actually expand your signal with respect to t axis, with respect to time. So in this case, you could see that now the time 5 is no longer 5, but whenever you have t over 2, is going to be 10 because you have to multiply by 2. And whenever you have time of minus 1, so you multiply by 2, that's why you get minus 2 in this case. So it is much easier to see that whenever you wanted to time scaling t over 2, so in this case I mentioned that a greater than 1, it is gonna be compression. Compression. But if a is lesser than 1, it's going to be expansion. So in this case, you are having a, this value, which is less than 1, which is you are having 1 over 2. So you could also imagine as, so let's say this is your new gt, your new function of t over 2. This is your original function, which is gt. So you are having triangular function whereby you have t of minus 1 and t of 5. So whenever you do time scaling for gt over 2, you could imagine that your new g prime, for example, a new function, now g prime function going to be 2. Whenever you bring it here, you have to be 2t. So that's why you need to multiply the t with 2. So now 5 you multiply by 2, you got 10. And the peak here somewhere at 4. So you have to multiply by 2, you got 8. And here t is minus 1, you multiply by 2, that's why you got minus 2. And please note that for time scaling, your amplitude gonna remain the same, which is 5. So let's see for the next. So next, now you are having a constant here which is greater than 1. So that's why we call whenever you have greater than 1, it is compression. So the same goes here. So whenever you have a new signal of y prime t, for example, which is equal to yt equal to x to t, you could think that your new function of signal, for example y prime here, is basically equal to t, 2 here you have to bring over here is going to be divide. So that's why you have to divide your t with 2. So here, same goes here, amplitude not going to be changed. You still have 4. And t now instead of minus 1, you have to divide by 2. That's why you got minus 0.5, or which is also equal to minus 1.2. And 3 here you divide by 2, you got 1.5, which is 3 over 2. So that's why we call now your signal having compression. So it's kind of like shrink to this smaller size. So again, you know that whenever a, the value of a is greater than 1, the scaling result is compression. And if a is lesser than 1, the scaling result in expansion. So next, you're going to learn about reversal and reflection. So notice that whenever you have reversal, you have a negative sign. So here, let's not look yet at the example as well as this definition. So let's say now you are having this signal. So you are having xt signal with let's say this is 5, so this is 2, and then you have another one which is -2 and -1. So you're having this kind of signal here as well as so this is 2 again, this is -1. So this is your signal. Okay. So let's say you have this kind of signal. So whenever you have reversal, let's say now you want to reverse the signal to pt, a new function whereby you are having x minus t. So minus means reversal. So now your signal no longer look like this. So you have to actually rotate this signal in a frame of 180 degree about this vertical axis. So now instead of this line here on this side, so that line gonna be on the other side. So you still have 2, but here you have -5 here. And then for the other part, 2 here, you have to bring to positive time, you got 2. And amplitude of course remain the same, -1. So you're having here. So you could think of the mirror function at the vertical axis here. So this is time reversal. So you see that whatever happened at some instant of t is gonna be also happening at the instant of minus t. And to time inverse, of course, we just replace the t with minus t. So for the example that being shown here, so you have continuous time signal that having reversal as well as the time scaling. So you could see here, this is time scaling, which is t over 2, and then you have the negative sign. So this is the time reversal. So now your signal is t over 2. Is it compression or expansion? You know that whenever a, the value of multiplier is lesser than 1, is going to be expansion. So that's why what you could do here is you could do it step by step. You could do first for this signal. You could do first the time scaling. So you know that for this new signal, it is g t over 2. This is expansion. So you know that instead of -1, now you have to multiply by 2. So now it's going to be -2. Amplitude not changing, still 5. And 5 gonna be 10. and then you have peak here at 4, so now it's going to be at 8. So here, this is your signal that having a time scaling, which is equal to gt over 2. So now, because you need to change to time reversal, you have negative sign. So you just mirror with this axis. So that's why you got now, instead of minus 2, you got 2 here. Instead of 10, you got minus 10. And peak here at somewhere at 8. Now it's going to be minus 8. So that's why your signal now look like this. So somewhat you mirror at the vertical axis. So same goes whenever you have a discrete time signal. So you learned before, right? You have CT signal, you have DT signal. So for discrete time signal, so you have this discrete amplitude at certain integer n. So now whenever you wanted to do uh, time reversal. In this case, there is no time scaling. It directly doing reversal. So you could see that you could basically, as I told you, you could basically rotate with this 180 with respect to your y-axis, your vertical axis in this case. So now you have to mirror. So that's why now you have 4 at 0. So now 1 become minus 1, so that's why you have 3 over here. 2 become minus 2, you have 2 here. 3 now become minus 3, you have 1. And then for minus 1 and minus 2 become 1 and 2 at 0 amplitude. So it is rather simpler, right? So now next we are going to see time shifting. So for time shifting, you have basically two time shifting, two condition whereby the first one is equal to x t a smaller t minus t, whereby the graph going to move to the right, or you could also say you are having the signal is having a delay, and the other one is basically t t minus t. So you could say your now the signal is going to move to the left. So you could say now you are having advance. So another example, let's say you have 0, then you have xt function signal t, and then let's say you have this shape of signal. So whenever you having a delay, you basically move those graph to the right. So this is your t. Now this is your t 0 0. So you basically move graph to the right. So in this case, your new function, which is let's say phi t, gonna be equal to x t minus t. Your signal now having a delay. So if your signal is moving to the left, for example, moving to the left, so this is your t. So you basically going to have x t minus t. because it is advanced, so that's why you have x t plus t. So you could see that your graph is moving to the left, advanced. This graph is moving to the right, we call it as a delay. And this is another example whereby you could see it, right? So in this case, you are having g t minus 1. So you have to move your graph or your signal here with one boxes. So whenever you move minus 1, no longer minus 1, you move 1 to the right, so it's going to be 0. 5, you move 1 step, so it's going to be 6. So now you are having this graph. So same goes for discrete time signal. Whenever you have a delay, you move to the right. So in this case, you move by 3 steps. So you could see that value 1 at 0 and equal to 0, you move 3. 1, 2, 3. So that's why you're having now so you're from here 1, 2, 3. So that's why you are having now the first amplitude of 1 at n equal to 3, the second amplitude of 2 at n equal to 4, and so on. So if you have a signal that is x n plus 2, you basically moving the function to the left. So this means that you are having an advance. So in this case, uh, 0, you move 2 steps to the left, which is because this is n plus 2. So 1, 2. So that's why you have now signal at amplitude of 1 at n equal to minus 2, and the other signal gonna follows. And we have as well here precedence rules. So there are two rules basically if you have multiple transformations. So in this case, you have AG, signal G, T minus T over A. So in this case, you have amplitude scaling. You have as well time scaling, which is you could see here T over A. And then you have as well time shifting, because you have the minus or plus function. Same goes for this one. If you this one is delay, time shifting for delay. This one is time shifting for advance. So whenever you have this kind of transformation, you have to do the amplitude scaling first, and then you need to do the time scaling, and then lastly you do the time shifting. So notice that if you have time scaling of a less than 1, you do time scaling first, then afterwards you do time shifting. But uh, it's going to be the opposite for signal. Let's say you have the amplitude scaling, you have the time scaling as well as the time shifting. But in this case, your time scaling, in this case, the value of A is greater than 1. So whenever you have time scaling that is greater than 1, what you should do is, of course, firstly, you have to do the amplitude scaling. Second, you can do the time shifting first. And later, lastly, you could do the time scaling. So it's the same, it's different with this one. Because this one you have to do the time scaling first and then time shifting. So let's have a look on the example here. So in this case, you have this signal of GT. You are having rectangular, basic rectangular function, right? Now you have the amplitude of 1, and time in between minus 1 over 2 and 1 over 2. So now you have this transformation minus 2g, this is amplitude scaling, and then you have t plus 2 over 4. So you have, in this case, time scaling, and then lastly you have time shifting. So first, according to the precedence rule here, of course first you have to do the amplitude scaling. So this is what you are doing, amplitude scaling. But notice that the amplitude scaling is not just amplitude scaling, but you have also reversal because you have negative. So that's why this one, if you do first the amplitude scaling, so it's no longer at 1 because you have to multiply by 2. So you have g t 2gt. You do first this one. So this is 2, this is minus 1 over 2, this is 1 over 2, this is t. And then next, because it is having minus sign, so you had to invert your amplitude. So instead of 2, now you had to invert, you have to apply negative at 2. Now you are having minus 2 over here. So t is not changing. So next, what you have to do is time scaling first because you are having a that is less than 1. In this case, you are having t over 4. So that's why you do time scaling first. So whenever you do time scaling, whenever you have a that is less than 1, in this case you have 1 over 4 value, it's gonna be the expansion. So as I told you, you could think of your signal whenever you have a signal of g t over 4. So your new signal, let's say this is new signal g prime t. So you could think of your new signal of 4 you bring over here, you had to multiply the t with 4. So this is your new signal. So that's why here the value of t minus 1 over 2, you multiply by 4, you get minus 2. And here 1 over 2 you multiply by 4, you get 2. So now we could say that your signal is somewhat being expanded with respect to t axis because it's no longer 1 over 2 but now it is 2. This is also no longer minus 1 over 2, this is minus 2. So lastly, when you did the time scaling, you do the time shifting. So time shifting in this case, you are having an advance because it is positive by 2. So that's why you have to move to the left by 2. So this one move by 2, that's why you got minus 4. 2, you move by 2, so you got 0. So now this is your final signal. So you have a signal of rectangular having amplitude scaling and reversal, as well as of expansion and also shifting. So next, let's say you have this signal of amplitude scaling and you have also time scaling and time shifting of minus 1. But now because your A is basically greater than 1, for time scaling, you don't consider the negative because negative here normally indicate the reversal. So you should do first, of course, uh, the amplitude scaling. So in this case, this is your signal, triangular signal with t of minus 1 and 1 and amplitude of 1. So whenever you had to scale the amplitude by 3. So 1 is no longer 1, you had to multiply by 3. So that's why now you have 3. And note that your time is still the same, which is minus 1 to 1. And then you do the time shifting. So right now you have t minus 1. In this case, you are having a delay by 1. So that's why you have to move the signal to the right 1. So minus 1 move 1, so that's why you got 0. And 1, you move 1, you got 2. So now this is your new signal. And then next, basically, if you do it one by one, next you have those time scaling. So time scaling here, you need to scale of G to T, for example here. So you need to basically for your G prime signal, you need to make sure T is divided by 2. So that's why now 0 divided by 2 equal to 0. So 2 divided by 2 equal to 1. So you have 3 here. So now this is your new signal, which is you're having 3 as amplitude. But now your time is from 0 to 1. So next, then you do this one, which is you're having minus G minus 2t. So you invert your signal here. So instead of t1, now t minus 1, you have to reverse. 0 remain at 0 and amplitude remain the same, which is 3. So now you are having this type of signal, which is the time inverse of this signal. Hopefully you could understand this or transformation of the signal before we go to the next slide. Uh, we're gonna take 5 before we go to the next slide. Okay. We are going to continue on the next subchapter, which is differentiation and integration. I do believe you basically have learned this in your high school, right? Differentiation, integration. Even right now, not really sure. I think you are taking engineering mathematics one, or even if you are a bit senior, you already took engineering mathematics one. Now you are taking engineering mathematics two, and so on. So you should at least, I guess, familiar how the differentiation and integration has been done. If not, then you have to revise on your own how you need to do the differentiation and integration. But right now, we are going to see a bit on how the differentiation as well as the differentiation for signal. So you have this question whereby you have first you have this kind of symbol, long stretch look like S. So this is integration. Whenever you have dx over dt, this is differentiation. So let's see first for the integration. So here you have the integration of minus 2 to 11 of function u for minus t. So you learned before at the very first few slide on this chapter that you know that u is a unit step function. So by definition, you know that u, let's say now you have u, ut is a unit step function, but I don't want to use t because you are having t here. Let's say I replace with alpha. So u alpha is equal to 1 when alpha value is greater or equal to 0, and u alpha is equal to 0 for otherwise. So recall that you know that unit step function, you have this, right? You have function with amplitude of 1 starting at 0. So now because I replace t with alpha, this is alpha. So this is u alpha. So this is unit step function. So if uh, so you know that now you have u for minus t is equal to 1 when for minus t greater or equal to 0. So this term here you could rearrange further, then you could see that you are having t that is less or greater than 4. And of course, for t, so for u minus t equal to 0, for t that is greater than 4. Because now your signal no longer start at 0, but it is something like this. You have 4, so you have a signal of 1, this is 0, this is u 4 minus t, so you have t. So that's why you have signal which is equal to 1 here when t is equal or less than 4, and the other part, like for example this part is 0 for t greater than 4. So you could now break this integration into you have integration of minus 2 to 11 of u 4 minus t dt. Now you could break the integration into, you know that minus 2 is somewhat here, right? So you're gonna have one function. So minus 2 to 4 of 1 dt, because this is equal to 1. In fact, the value here as well 1. Then you have to plus with 4 to 11, because the total integration is from minus 2 to 11 of 0 dt, because from 4 t equal to 4 or greater than 4 onwards is 0. So now it is much more easier, right? So you do integration of 1, so you get t, and then you need to solve for from 4 to minus 2. Then integration of 0 gonna be 0. So for this part, you replace t with 4. So 4 minus 2. This is for this part here. Then plus 0. So that's why in the end you have 4 minus 2, you have 6. So this is the answer for the first question A. So how about question B? So for question B, you have those differentiation of dx dt of function 1 minus exponential minus t. So how you do it? So for this, now question B. So what you can do is you could regard xt, which is equal to 1 minus exponential minus t, ut. So what is the value for d dt of xt? Because remember that I told you whenever you want to make the signal starting at 0, you have to multiply by the step function. So remember that you have a product rule whereby you have xt equal to ft ut. So now x prime t is equal to f prime t ut plus ft u prime t. So u prime t here is the derivative basically of derivative of the start. So we could also say that this is u prime t, which is equal to delta impulse. So ft here is this one. So ft is 1 minus exponential minus t. And of course, you need to find f prime t, which is in this case equal to d dt, derivative of this function with respect to t. D dt of 1 minus exponential minus t. So again, try to look back at the derivation rule for exponential. So what you got is basically the same term of exponential, which is minus exponential minus t, but you have to multiply the constant for the t, which is minus 1. So that's why in the end you have exponential minus t. And of course, therefore, you could again represent this x prime t equal to exponential minus t. This is the f prime t that you solved earlier. You got exponential minus t multiplied by unit step ut. So plus this term again, ft, that we regard as 1 minus exponential t, multiply u prime t is basically the delta impulse. So multiply delta impulse. So delta impulse at 0. So this term at t equal to 0. So you need basically to replace t with 0. So whenever you replace the t with 0 for this term here, so you replace 1 minus e, t is 0, exponential 0, multiply those impulse term. So what you got is basically exponential 0 is 1. So 1 minus 1, what you got is 0. That to multiply by those impulse, delta impulse. So that's why this is going to be cancelled, because 0 multiplied by whatever term you get, you're going to get 0. So that's why you could simplify this x prime t. So in this case, x prime t is dx over dt, which is equal to exponential minus t ut, because this term is basically 0. So that's why you got the answer of exponential minus t ut. So that's the example of how you do differentiation and integration for signal. Maybe for the next coming lecture, we're going to see more operations on signal as well as during the tutorials, but this is some of few basics operations. Hopefully you could recall what you have done with derivation, integration and all, so that you would be able to do integrations, all those operations later on. So as a conclusion, uh, now you basically know how to play around with the signal. So you can do amplitude scaling, time scaling, what other? Time shifting, reversal, amplitude reversal, time reversal, and whatnot. And then, of course, in mathematical formulation, there will be some rules to be applied. So you had to be aware of that. So that's going to be the end for this lecture. So next week there will be no lecture on Monday, because it is public holiday. So you can refer to the e-learning. I basically uh, also note there that there is no lecture on Monday. On Tuesday, I'm probably not gonna do online lecture. I'm gonna do recorded lecture, and then I'm going to upload in your e-learning. Okay, so please make sure you have a look on the videos anytime you are free. So I believe only our Indian friends who actually going to having Deepavali celebration. So the rest of you, you can view the video at any time. So the video gonna be uploaded after Monday, because Monday is public holidays. So that's all. If you have any question, please ask. If not, you may leave the session. Thank you so much for your attention.
Okay, thank you, Doctor.
Thank you,
Thank you,
brother.
Doctor.
Thank you, doctor.
Thank you,
Thank you,
madam.
doctor.
Yeah, you're welcome.
Thank you, madam.
Bye-bye semua.
Bye bye. Happy holiday. Happy Deepavali to Indian friends.
Thank you so much, doctor.
Indian,
Thank
yes.
thank you, doctor. Come to my home, doctor, to
Thank you,
celebrate.
madam.
Thank you, madam.
Okay. Bye bye.
Bye.
So you may leave
Thank
the
you,
session.
madam. Thank you, madam.
Yeah, you're welcome. So bye bye. I will wait for a couple more minutes. If you have any question, if not, you can leave the session. Thank you.